All right, so when we talk about the addition rule, this section presents the addition rule as a device for finding probabilities that can be expressed as the probability of A or B, which is the probability that either event A occurs or event B occurs, or they both occur. The key word in this section is or. This is the inclusive or, which means either one or the other or both. So mathematically, unless we tell you otherwise, when we say the word or in math, it's one happens or the other happens or they both happen. So you're really focusing on looking for the word or in these problems to recognize that we're going to use the addition rule. So, compounding event is any event that combines two or more simple events. So remember last time we talked about those simple events being those events that we could not break down any further. Well, this is combining two or more of those. So if we were rolling a dice and flipping a coin and finding the probability that I flip a heads and I flip and I roll a 2 at the same time, or that I roll a 2 or flip a heads. Those would be different kinds of compound events. And again, whether I'm saying the word or the word and is going to make a difference in the way we combine these different simple events. And today we're going to focus on the word or as we're doing things. So, oh, you know what? I was just saying things slightly wrong when I'm doing this one. This would be more of a flipping or rolling a dice and wanting the probability I get a 2 or a 3 as I'm doing it. You're looking at two or more of those simple events that we're trying to pull out of there as we do things. So our notation is the probability that A or B means that the probability that in a single trial event A occurs or event B occurs or they both occur. No, I was right the first time. This would be the probability that we roll a dice and we get a 2 or we flip the coin and get a heads would be what we're looking for. Be one of the ways that we can have these. Formal addition rule. So if we're working on doing these and we want to go through and just have a straightforward way of calculating things, the probability that A or B occurs, we take the probability that A occurs plus the probability that B occurs, and we subtract off the fact that there's sometimes that they're both going to occur. Because if I'm looking for the probability that both A and B happen, then I've counted A here, I've counted the same thing here, and you can't count the same thing happening twice. And so where the probability of the probability that A and B denotes the probability that A and B both occur at the same time as an outcome in a trial of a procedure. So looking at an example and following through with doing the formal addition rule as we do this one. We look at number 30 on page 158. So this is our survey refusals. What is the probability that the selected person refused to respond or is over the 59 years of age? And so we've got the little table above here. This is a study of people who refused to answer survey questions where we had their different ages. We have whether they responded or whether they refused. And so now, if I want the probability that the selected person refused to respond or is over 59 years of age. So if I'm wanting to do that, the way I'd be writing this to begin with, we're going to find the probability they refused or they're over 59 years old. We're going to find the probability that they refused plus the probability that they're over 59, and we're going to subtract off the probability that they're both. So this is looking at using that formal addition rule as we do it. Well, what's the probability that they refused to answer? How many people refused to answer my survey? How many? Okay, and how many people were in our survey? Did it tell me on here? I think it's 1205. Yeah, it's 1205. Thank you. Oh, and I about forgot to start sending around the homework. There's 2 or 3 assignments that are in here. So we had 156 out of the 1205 that refused to answer. What is the probability that somebody's over the age of 59? Over. Altogether. 251 of them out of the 1205. Now, what you're trying to give me is what's the probability that they're both? That's your 49. Because there were 49 people that were over the age of 59 that refused to answer. Questions on what I'm setting up so far? Now, as you do this, then, if we add the 156 plus the 251 and subtract off the 1205, we're going to get 358 out of the 1205. This is one time where leaving it as a fraction really isn't that helpful because my mind doesn't really get a good idea of, well, how many is that? What value? So if we turn this one into a percent, then you're going to get the 0.297, which is the same as the 29.7%. So you can either, this is one where we would either leave it as a decimal or change it into a percent. Decimal would be a good way of leaving this probability. Questions there? Now, if we're well, I won't jump ahead. Questions on what we're doing here? Questions why we had to subtract off the 49. Okay, those people were counted twice. Those people were counted in the refused. Those people were counted in the over 59. They're not that important that they get to be counted twice, so we had to subtract off those values that were already being counted twice as we were doing it. So your formal addition rule makes common sense when you really stop and look at what you've got going on with it. Now, we also have the intuitive addition rule, which is still finding that probability that A occurs or B occurs. This is where you find the sum of the number of ways event A can occur and the number of ways event B can occur, adding in such a way that every outcome is counted only once. So you're finding the probability that A or B is that sum divided by the total number of outcomes in your sample space. So if we were looking back at number 30 again, we already know from what we did a little bit ago so we're still trying to find the probability they refuse or they're over the age of 59. We know from before that if we found the probability they refused was going to be 156 out of 1205. If I wanted to look at my chart then and just figure out what else I need to add on, if I'm trying to figure out those people that are over the age of 59, we already know 49 of them still refused. Well, that 49's already been counted, so what else do I need to add in? I need to add in that 202 people that are also over the age of 59 but that answered, because those guys haven't been counted yet. And so when you add it in, you're just adding in such a way that you're not counting the same group twice. And so, just let me rewrite this the way I'm going to write this problem. So we would add it in such a way that we would take that 156, we'd add in those 202 people to figure out the number of people that refused or were over the age of 59 and didn't refuse. And then we're dividing it by the total number, which was the 1205. You still get the same answer of 358 out of the 1205, which still gives me the same decimal of 0.297. And remember, as you're rounding probabilities, round those to 3 decimal places, which if you think about it, when you move that into a percent, it becomes 29.7%. Having that one extra decimal giving you that extra information. Questions on that one? I'll do another one. I want you guys to do this one on your boards. So your sock drawer is a mess. There are 12 black socks and 6 red socks mixed together. What are the chances that, without looking, the one sock you pick out of the drawer is a red sock? And what are the chances that, without looking, the one sock you pick is a black sock? Thank you. That was not a very good example of what I wanted. So what's the probability that you pick a black sock? Oh, I'm doing my board. What's the probability to pick a red sock? Let's go with red first. What's the probability to get a black sock? What's the probability to get a red or a black sock? Okay. It's not my or that I really was wanting to have. But I had a better problem on here. Well, okay, that one's not such a good problem. Let's do a different one. Out of our deck of cards, what's the probability that I will get a king or a heart? And convert this one to a decimal. Yeah, make this one a decimal. All right, I saw both ways being demonstrated out here. First of all, if we do that with the formal definition, probability that we get a king plus the probability that it's a heart minus the probability that it's both. So what's the probability we get a king? What's the probability that that's supposed to be a heart? What's the probability that's at a heart? Do we have any that's both? Yeah, the king of hearts is both, so we have to subtract off that one card that's both. And so then we're looking at 4 plus 13 minus 1 gives me 16 out of 52. Which rounded to, well, we'll come back to that. The other way that I saw some of you guys looking at doing this was you said we had 4 kings, plus if we're looking at the hearts, there's 13 hearts in a suit, but one of them is the king of hearts, so we've already counted him. So you only had to add on 12 more out of our 52. So you still get the 16 out of 52. And if I change 16 out of 52 into a decimal, we get 0.30769. So rounded to 2 decimals is going to be 0.308. Now, what if instead I asked you for the probability that it is a king or a queen? I'll go ahead and just do this one as a fraction. reduce your fraction gauge. It's not. I'm making things up. So now we're doing the probability it's king or queen. So if I'm doing the probability that it's a king plus the probability that it's a queen minus the probability that it's both, what's the probability we have a king? 4 out of 52. Probability of queen? Probability that it's both. Okay, there's not any cards that are both a king and a queen. It's either a king or it's a queen. There's not any overlap. So you're looking at having 8 out of 52. So when I'm taking and counting them in such a way that there's not any that are counted twice, I didn't have to worry about that this time because there wasn't any overlap. Now, 8 over 52 can both be divided by 4 to get 2 out of 13, which still makes common sense. Each suit has a king and a queen. So there's 2 of those, either a king or queen, in each of those suits. Okay, questions on those? Now, this last one was an example of things that are disjoint or mutually exclusive. Events A and B are disjoint or mutually exclusive if they cannot occur at the same time. That is, disjoint events do not overlap. Probability that it's a king or the probability that it's a queen did not have any overlap between the two. There's not any way to be both at the same time. Versus most of the time when we look at these, we have some overlap. The probability that it was a king or the probability that it was a heart, we had the king of hearts that was in here in the overlap area. And so when you're looking at these things, having that Venn diagram to kind of help express what we're looking at. Where the total area has to add up to be 1, and when we talk about the total area, it's the entire box. So those cards that didn't fit either one of them would be the ones that are out there in the white around the edges. So when you're talking about those things that are disjoint, they're not both going to happen at the same time. Okay, I want you guys to go ahead and find this one. Find the probability of rolling a die and getting a multiple of 3 or rolling a 2. So if I'm looking at being a multiple of 3, what numbers are your multiples of 3? Okay. Is there any overlap with, well, and if rolling a 2 would be a 2. Is there any overlap on those? No. So when we look at how many options we have 3 ways we can roll it. Out of how many ways can I roll a dice? So 3, 6 reduced down to being 1/2. This is an example of something that's mutually exclusive. These are disjoint events. There's not any way that you can get both of them at the same time. Now, it still leaves me other options. I'm not looking at all possible other options being listed, because you could still just roll a 1 and not meet either one of those criteria. But there's no way to have both of those things happening simultaneously. Now, when we talk about complementary events, these are even more specific than just being disjoint. Disjoint means they can't happen at the same time, but there might be other options. Complementary events is looking at the probability of A happening or the probability that the complement of A is occurring. Remember when we talked about A bar, that's saying it's everything that's not A. Well, these things are disjoint, meaning it is impossible for an event and its complement to occur at the same time. So if A was that I was going to roll a 2, what would A bar be? Okay, we could roll a 1, 3, 4, 5, or 6. That is just looking at the fact that I'm not rolling a 2. Well, when we talk about that then, what do you think is going to be true about the probability of A and the probability of its complement? Say it again, Shelby. They're going to equal 1. If we add those two probabilities, it's either it's going to happen or it's not going to happen, there's no other options when we talk about those. And so when you talk about the probability of A and its complement, they're disjoint, but that also tells me then that they have to add up to being a total of 1. So the probability that A occurs or its complement occurs is going to always add up to being 1. That's more helpful when we look at it the other way. If I know the probability that it doesn't happen, then, if I know the probability that it does happen, I can take 1 minus that to find the probability that it does not happen. Or if I know the probability that it does not happen, my bar got scooted over, then I can take 1 minus that to figure out the probability that it does happen. Questions there? So that's going to help us as we try to figure out those questions, well, kind of like the problem that we were looking at earlier when we were saying that, making our best guess on the probability that we would be slowed down due to an accident. Well, if I had a good guess of what the probability was that I was going to be slowed down, to figure out the probability that I wasn't slowed down was the opposite of that. It was 1 minus that value. Because I had to total up to be in that 100% chance. So let's look at number 14 on page 157. Let's talk about color blindness. Women have a 0.25% rate of red-green or red-green color blindness. If a woman is randomly selected, what is the probability that she does not have red-green color blindness? 14. So my probability that I'm colorblind is 0.25% chance that a woman's colorblind. If I want to find the probability that I am not colorblind, (99.75) what? Okay, percent's important on there. So if I'm asking for it as a decimal, trying to find the probability, first of all, what's 0.25% as a decimal? Okay. So to find the probability that I'm not colorblind, or that a woman is not colorblind, we would take 1 minus the 0.0025, which, as Aaron pointed out, was that 0.9975. Or 99.75% chance. So the probability that a woman's colorblind is very, very, very slim. Probability that a man's colorblind is a lot higher. But notice that this is kind of a back door to be able to find your way in to figuring out what those probabilities are, because it's a lot easier to find the probability that somebody's colorblind. That's going to be researched and reported. Trying to find the probability that you're not colorblind, then you kind of have to work your way backwards to get that. So when we talk about the Venn diagrams then for complementary events, then the probability that A occurs would be my yellow blob. The probability that A does not occur would be this pink part. That's that complement. Altogether, they have to add up to be 1. It's either going to happen or it's not going to happen. They're still disjoint. There's no overlap between the fact that it does happen or it doesn't happen. There's not any overlap on those, so they're still disjoint, but it's even more specific than just being disjoint. So disjoint is when they can't overlap, but when you're talking about complementary, then there's no other options. It either is or it is not. Questions there? Oh man, we're getting done early. I really think I am done though. Enjoy being done really early today. I'll try not to do this to you much more. I'll try to use you guys' time up a little better. Okay, I'll make sure I take care of that for you, Aaron. No, I really do feel bad when I get done this early. But I will make up for it other times when I'm like running you guys a minute or two late. Just remember, I had 12 minutes of makeup time in here. You don't think